Hello everyone and welcome back. So today we are going to cover the naive Bayes algorithm. Previously we saw how we can implement the k nearest neighbor algorithm and we have some results of it. Today we are going to understand naive Bayes, implement it and see what is the difference when we apply naive Bayes to the same example. So before we jump in and apply naive Bayes, let's first understand the concept behind it. So in probability, to understand the naive Bayes algorithm, we first need to understand the naive Bayes theorem. And in probability, Bayes theorem is used to determine the conditional probability of the given event. Now, if we try to understand this with the help of this equation, you can see that we have to calculate the probability of A, and this sign over here is to show you given, meaning that we have to calculate the probability of A given that B has already happened, meaning that this condition has already occurred, and we have to calculate the probability of A given that B has already occurred. So if we want to calculate this probability, we have this equation over here, which is to calculate the probability of B, the probability of event B, given that A has already happened. This is what this actually means. Multiply by the probability of A and then we divide it by the probability of B. So using this formula, we can calculate the conditional probability of this, given that this event has already happened. So to better understand this, I have added this example which I found on YouTube and I found it to be really useful. So that's why I've added here as well. So in this example, we have bag 1 and bag 2. As you can see over here, this is our bag 1 and this will be our bag 2. Okay, simply. And in bag 1 we have 2 red balls and 3 black balls. In bag 2 we have 4 red balls and 3 black balls. So first of all, let's first calculate the basic probability, so we have something to work with and apply the naive Bayes algorithm to it. So for example, what is the probability out of these 2 bags that we will select bag 1? So for example, we have 2 bags. What is the probability that we are going to select bag 1? The probability of this will be 1, right? Because we have 2 bags, the probability of selecting bag 1 is 1 by 2. Similarly, if we calculate the probability of selecting bag 2, this will also be 1 by 2. Okay, now this is out of the way. Next, we are going to go back to bag 1 and now we are going to see what is the probability of having red ball. If we put our hand in this bag, what is the probability that we'll get a red ball out of all these balls? So the probability of taking out a red ball is 2 divided by what is the total number of balls? 2 plus 3 is equals to 5, right? This is the probability. Similarly, we are going to do the same for bag 2. What is the probability of taking out red ball from bag 2? Which this is 4 divided by 4 plus 3 is equals to 7, right? Now, these are the probability that we have calculated so far. So, according to Bayes' theorem, we have this condition. We have this event that has already occurred, which is B, and this is the probability A, based on this equation that we just covered. So we have to calculate the probability. If we look into this question, we see that one ball is drawn randomly from one of these bags, and it is red. What is the probability that it is drawn from bag 1? So we have to find the probability. We already know that the ball is red. We have to find the probability that this ball belongs to bag 1. So if we put this thing into equation, we can see that we have to calculate the probability of bag 1 given that the ball is already red. The event has already occurred. So if we put this into the equation, we have to first calculate the probability that the ball is red given that the bag is 1, multiply the probability of bag 1 and divide it by the probability of red. So if we put the values into this equation, if we see what is the probability of ball being red in bag 1, it is 2 by 5. So this is what we put here as well. Then what is the probability of bag 1? That's 1 by 2 that we just calculated over here. And then we have to calculate the probability of red, meaning that what is the probability that both of these bags have red balls. So to do this, first we are going to take the probability of having bag 1, which is this one, multiply the probability of taking out a red ball from bag 1, then multiplying it with the probability of selecting bag 2, and then multiplying it with the probability that the ball that is taken out from the bag 2 is red. which is 4 by 7. So solving this equation will give us the probability and solve this question that what is the probability that the red ball is drawn from bag 1, we'll get it when we solve this equation. So this is how the naive Bayes theorem works. So now moving on to naive Bayes classification, I have added another example for that to make it easier for you. So before we jump into the example, first let's go through how the equation will change when we are working with a classification based problem. So basically, when we are working with a classification problem, for example, the easiest of which is the binary classification, what we have is that we have to find the probability of two things. If the category is yes or if it is no. So for example, we have some features, and based on those features, we have to calculate if the person has cancer or if he does not have cancer. So for that, we have these two equations like this, right? Now, if we open up this equation, we know that in real world, we don't have only one feature, we can have multiple features, right? So this X represents our features, and this is the prediction that we need to make. So we have to calculate the probability that a person has cancer given that these are the features that we have been provided. So for example, his age, his previous medical records and everything. So to solve this equation, what we need to do is that we need to find the probability of each feature given that the event has already occurred, and then we multiply it with the probability of this prediction divided by the probability of the features. Similarly, for the new category, we'll repeat the same process. We'll multiply each probability with this prediction like this. Okay, and then we multiply it by the probability that the person does not have cancer divided by the probability of these features. So one thing that is common in both these equations is that the denominator is common, right? So if we solve this denominator and if we skip this denominator, it won't make much difference, right? So we can only focus on the numerator and solve this equation, and we can skip this denominator and we'll still get the same answer. So it is to make things easier for you. If you want to solve this, you can go ahead and do this, but for simplicity, we can take the denominator only for both of these and solve it and get the answer. So to better understand this, here is another example. This is basically a classification example where we have a person's information. We have 10 people, and then we have the information if the person has COVID or not, if the person has flu or not, and based on these two features, for example, we can call this x1 and we can call this x2, and based on these two features, we have to calculate if the person has fever or not. This can be our y, right? So we have these two features and we have this. Now we have this question, which means that given a person has flu and COVID, what is the probability that the person has fever? So given that a person has flu and COVID, we have to calculate the probability that the person has fever. So if we put this into equation, we already know that the person has flu and COVID, and we have has flu and COVID, meaning that the event has already occurred. We have to calculate if the person has fever or no fever. So it is a binary classification problem. So we have to calculate these two probabilities, right? One is that the person has fever, another is that the person does not have fever. And to solve this, we are going to simply take the denominator as discussed over here as well. We are going to take each feature and then take the probability of it given that the person has fever, multiply the second feature, which is COVID, given that the person has fever, and then we multiply it with the probability that the person has fever. So the step one for this is to calculate the prior probabilities, meaning that we first have to calculate how many people out of these 10 people have already have fever and they do not have fever. So total we have 10 records, and people who have fever are 1, 2, 3, 4, 5, 6, and 7, right? These are the people who have fever. Though the prior probability will be 7 by 10. And the people who do not have fever will be 1, 2, and 3. So 3 by 10. Next step is to calculate the conditional probabilities. Before we jump in and solve this equation, it is a good idea to first calculate the conditional probability and the prior probability so that it's easier for us to put all the values in the equation later on. So to calculate the conditional probability, first of all, we are going to take the patients who already have fever, which is these 7 patients, and then we have to see if those people also have COVID. So we have to see if the person has COVID given that he already has fever. So the person has already has fever, he already has COVID. 1, he has fever in COVID. 2, he has fever in COVID. 3, and then he has fever in COVID. 4. So the probability is 4 by 7. Next, we have to calculate that the person does not have fever and does not have COVID. So these are 3 records which do not have fever. So I'm going to check those. So for example, if the person does not have fever, the person does not have COVID. The person does not have fever, the person does not have COVID. And then one more entity. So there are only, for example, 2 entities that show that the person does not have COVID and does not have fever, which means that we have 2 by 3 probability. Similarly, we are going to repeat the same process for flu as well, and then we'll get the conditional probability. So for example, we'll calculate if the person has flu and has fever. So for example, person has flu and has fever 1, he has flu and fever 2, and he has flu and fever 3. We have to calculate these 3 probabilities. 1, 2, and 3 people have flu and they also have fever. So this will be 3 by 7. So this is how you calculate the conditional probabilities. So once we have the conditional probabilities and the prior probabilities, we are then going to put them into this equation we just calculated, which is that the person has fever, which is yes, given that the person has flu and COVID. We put all these values into this equation, and then finally we get this value. Similarly, we are going to put those prior probability values and the condition probability values over here. For example, the person has flu but no fever. Has the person has flu, given that the person does not have any fever, which is 2 by 3. We are going to put these values over here as well. So finally, if we see that we have to take the probability that is greater than the other one. So for example, the probability of having a fever is 0.17, and the probability of not having a fever is 0.13, which means that the person having a fever, given that he also has flu and COVID, is greater than that of the person who does not have fever, given that he has flu and COVID. So this means that this probability is higher. This means that the person has fever, given that he has flu and COVID. So this is how the naive-based classification works. Next, we are going to see how we can implement this and get the results. So let's move on to the coding part. Okay, so the coding of naive-Bayes is pretty straightforward and simple. I'm going to go through this data set, and I have explained how we can pre-process it and get it ready. So you can go back to the video and check it if you haven't already. So what we have simply done up until now is that we have added a few libraries, read the gamma telescope data set, then added the labels to it. Next, we and try to understand the data pattern using this histograms. After we have analyzed all these features, the next step is to get the data ready. For that, we have to do the training, validation, and test split. So before we do that, we first checked if there is some imbalance in the data, and we found that yes, the data set was imbalanced, meaning that the gamma samples were much higher compared to the hadron samples. So to resolve this, we defined a function where we first added a standard scaler, which would scale the values so that the values are in a certain scale, so that equal feature importance is given to each feature. Next, we have also added this random oversampler to solve this data imbalance and make sure that the hadron sample has the same amount of features as gamma sample. So the next step was to apply this and identify all these train, validation, and test set and get the data ready. Once the data set was ready, we then used the k nearest neighbor and we got these results. You can also check the video on this, how we applied this and what is the concept behind it. Now, next thing is the naive-Bayes algorithm. The naive-Bayes algorithm is pretty straightforward to apply. First thing is to read from the sklearn.naive-Bayes, we import the Gaussian naive-Bayes. Then we have defined a variable in which we have called this function, and then we simply apply this model by using this fit function, which takes in the x train and y train, where x train is the features and y train is the labels. Now the model is implemented, and the next thing is to calculate the prediction. We can predict using the model by using this dot predict function, and we have used this x test data set because we have kept data set to evaluate the performance of this model, because it is the unseen data and it allows us to generalize our model. So finally, if we look into the classification report, these are the few simple lines to imply this. And then finally, if you look at the classification report, you can see that the accuracy of this one is 0.73, which is, I think, less compared to that what we acquired from KNN. Like, as you can see over here, the accuracy that we acquired using KNN is 0.82, and it has fallen significantly if we apply this naive Bayes algorithm somehow. So next thing is that if we plot the heat map, we can see the true predictions, that the actual prediction is, for example, gamma, and the predictions that are made by the model for gamma are 2236, and for hadron the actual predictions and the predicted predictions are 533, which is less compared to that made by our KNN model. KNN model was able to identify the hadron samples in a much more effective way compared to these naive Bayes. So I have added this here as well to better show you the results. For example, if we compare the heat map side by side, you can see that the hadron samples have been predicted much more effectively in KNN compared to this naive Bayes. So this is how the naive Bayes basically works. I have tried to cover the concept behind it and how we can implement it, so that we can use it later on in our other projects as well. So I hope you like this video, and in the next one we are going to see how we can apply logistic regression and if it has any effect on the data, and if we can get better results by using it. So thank you so much for watching. I'll see you in the next one.